Yeah, so hello everyone. Yeah, so the next speaker is Yifeng Teng from Google Research. He was a student of Shuchi Chawla at Wisconsin, and he's been doing like a lot of online resource allocation. He's been at Google for a while now. Although he's in the hotel, unfortunately, he tested COVID positive this morning. So he's presenting, yeah, from here. Yeah.
Yeah.
Okay,
Yeah.
Yifeng, yeah, you can start.
Oh, okay. So can you hear me? Okay. Okay. So hello everyone. I'm Yifeng Teng from Google Research. Thanks Sahil and Andres for inviting me. So unfortunately, I just tested COVID positive and having fever this morning, so I cannot go downstairs, although I'm just upstairs. So yeah, so like hope that I'm actually talking about something reasonable today. The objective of the talk is on online welfare maximization, and the algorithm designer wants to maximize the total value obtained by the buyers. And in the offline setting, the welfare maximizing mechanism is well studied. So like the VCG mechanism can already get the optimal welfare and is a truthful mechanism. And the online setting is less studied. And in this work, we're talking about a online interval scheduling setting where suppose that we try to motivate with the cloud service provider having multiple machines that want to rent out to the customers to run their jobs, and the customer will arrive at a time where their specified job requirements for early reservation, maybe it's worth more value for the buyer, and for later reservation, it may have a different value. So we want to compare. We want to have a competitive analysis, which is competing against the optimal value in hindsight, which is just the offline optimal. So one example is like this. So we discretize the time into time slots, and those time slots are treated as items. And here the curve actually shows the number of machines available at every time. And suppose that the first buyer comes and has a value 100 for the first 3 slots and 80 for the last 3 slots. And suppose that we're using a greedy algorithm, and then she is allocated first 3 slots. Then the second buyer arrives, he has value 50 for the first 2 slots and 20 for one of the first 2 slots. And we can allocate the second slot to the buyer. And the overall welfare we get from the algorithm is 120. And we are competing against the optimal offline allocation, which is 130. So another more general setting, which actually I'm not going to talk a lot today, is online path allocation on graphs. So it's that the seller would like to sell the edges on a graph network, and each buyer demands a path on the graph. So the seller is going to have different capacity for each edge to sell, and the problem can be motivated by network allocation or ride-sharing economy. And I'm only going to mention some of the results, but due to the time constraint, I'm not going to go into details. So we noticed that interval scheduling problem on the path graph is just a special case of this on a very special type of graph. So for the interval scheduling problem, we discuss, I'm going to talk about 2 type of valuation function of the buyers. So first is the Bayesian setting. So the Bayesian setting, as discussed by Sahil and Andres yesterday. So the buyers will have possibly random values for different time intervals, and the distribution is known to the scheduler. We want to ask the question that what is the asymptotically best online algorithms for this problem, and can we even make it truthful? So the way we solve this is actually via balance price. So if any of you are here yesterday, you may have heard of this from Andrew's talk. And the second setting is a more restricted setting. So the more restricted setting, we consider the single-minded setting where the buyer just have fixed values for the intervals. And each buyer only demands a single interval and arrives with probability 1. So there is actually no uncertainty here. But the question we want to ask here is that can item pricing route the best allocation in the online setting? And during those item pricing mechanism, we need to take care of the tie-breaking power of the seller and the buyer. And these item prices are computed partially due to the dual prices which was introduced by Sahil yesterday. Okay, so now I'm going to talk about the first setting where we have the Bayesian setting, and we want to apply bundle pricing mechanism to see what compare ratio we can get against the offline optimal. This is joint work with Shuchi Chawla from UT Austin and Ben Miller from Google. So let's first look at some previous results. So like for this previous results, the first result to know is that for item pricing, if we assume that L is the length of the longest drop and K is the number of resources for each item, yesterday, Andres actually mentioned that the best approximation you can do is just a theta L approximation. So this is via item pricing. And suppose that you are allowed to use any online algorithm that do not necessarily need to be a mechanism. You do not need to have the truthfulness. Like Eman 1 Solo 11 shows that for single-minded buyer with unit capacity, there exists some randomized algorithm with log L approximation to the optimal offline. And the lower bound result is omega log L over log N. So if we only have a single item, so like if we only have a single item, then Allay has a sequence of work showing that the compare ratio starting from a single supply to be 2, and for the large supply setting can have a 1 plus minus approximation. This is similar to what described by Sahil yesterday. And for large supply setting, if you have a fixed value interval, then Chao et al. Showed that under some additional assumption on values for large supply, you can also get 1 plus epsilon via item pricing. So the work I'm going to talk today is to use static bundle pricing. Static bundle pricing to get a log L over log L approximation, assuming that there's only a single item, a single resource available for each item. And this actually matches the previous lower bound result. So this is actually asymptotically the best thing to do. So compared to any online algorithm. And we also show that when the supply increases, the compare ratio actually decreases accordingly. And we have a almost matching lower bound result for this. So the static bundle pricing, we show for those time slots, it's just some kind of mechanism like this. So we sell those time slots as bundles. Suppose that 1 hour time slot is a single item, then we see in this menu, the first slot has price 30, second slot has price 40, last slot has price 50. They have different capacity, and all the 3 slots have price 100. So to be more precise, we show that the anonymous bundle pricing gives a log L over log L approximation. This is tight and matches the previous lower bound. So this was the first online algorithm that gives a tight compare ratio, and it proves that there's no asymptotic gap between pricing and online non-truthful and randomized algorithms. And for the large market constraint, we show that the approximation ratio almost decreased linearly with respect to the capacity. So I'm going to show the results on some tree graphs for the selling passes on general graph, there are actually computational hardness results. So for tree graphs, suppose that we have the H to be the range of values, we are able to show that anonymous model pricing gives a log H approximation. So why do we consider the range of value and have approximation result using this? Because that we show that no online algorithm actually can give a sub-polynomial approximation with respect to the number of items. So this can be seen as a hardness result that for the interval setting you can do sub-polynomial, but for tree you cannot. So we described yesterday Andres had some example, but I'm not going to remind you like why I'm actually not using item pricing. Because the profit inequality proof via balance price, this shown by Andres yesterday for XOS valuation, needs to have so the buyer need to have no complementaries in valuation. So when they prove the profit inequality by balance price, you can show that the welfare is partitioned to two parts. One part is the revenue from the items, and the other part is from the utility of the buyers. And if you properly set the balance item price, when a buyer arrives and gets allocated to some item in she gets allocated in optimal, either the item is sold, contributing a lot of revenue to alg, or the item is still available, then the buyer is going to contribute a lot of utility. So in the interval setting, so it's possible that one buyer arrives demanding only a single item, just blocks the buyer that demands a long interval. So like for example, suppose that I have one buyer that wants to purchase one of the L items here, and with same value 1 for each item, and the other buyer has value L minus 1 for the entire interval. So if any of the item has price 1, below 1, I'm going to let the first buyer arrive, and it's going to block the second buyer. So this means that if we set a low enough price for any item, you cannot do better than 1. But if you set a high enough price for every item, the buyer that demands the entire interval cannot afford to purchase this. So this is an example showing there's a tight omega L approximation via item pricing. So we can write down the fractional relaxation of the problem. We can use it as an upper bound for the optimal solution. And what we learned yesterday is that for unit demand buyers, where the buyer demands one of the item pricing can actually obtain a half of the optimal in welfare. And actually we can so like the same proof can show that item pricing obtains a half of the fractional optimal, which is just the value of the fractional relaxation in welfare. So we want to use this just as a black box. So the idea of reducing the interval scheduling problem to the unit demand buyer setting is to partition all the item to meta items, and assume that each buyer only wants to purchase one of the meta items. And we apply the profit inequality for the unit demand buyer on those meta items, have bundle prices for the meta items. Then this gives a constant approximation to the linear program relaxation for the fractional unit allocation. So the meta item partitioning actually works as follows. So suppose that this is a fractional solution of the original LP. And the way we do this is just we have T1, T2, T3 to be the meta items. They each represent an interval, and we partition this the fractional solution, the jobs to multiple groups. Each group of buyer demands the interval that is contained in the corresponding meta item with total allocation at most 1. So this is just reduction to the unit demand over these meta items. So we want to have this kind of meta item partitioning that do not lose much revenue. Sorry, do not lose much welfare. So now, actually, we just have a pure algorithmic question. So we want to do the meta item partitioning and consider a new fractional unit allocation and have the corresponding fractional solution over the meta items. And can we have a good partitioning such that the new fractional solution have a good value compared to original LP value? So we show that it's doable if all buyers demand intervals of length L, there exists a fractional unit allocation that obtains at least log L over log L fraction of the original LP. So I'm going to briefly describe why this is true. We consider a special example where we have a unit capacity case and the jobs are aligned perfectly. Each job just have length power 2 and they are aligned like this. So a log L approximation is actually pretty easy. So like there are only log L levels of jobs, and we can try to extract the value from jobs at one of the level, and this gives a log L approximation. So the question is that can we do more? The way we do more is to first divide all jobs to 3 parts. The first part consists of low-value jobs, such that the value of job is smaller and half of expected welfare contributed from the item in the job, and they have low contribution to opt. And the second part is the high-value job with high allocation. If the job has allocation at least log L over log L, I'm going to sell at the topmost level, and this actually gave a so this actually gave a log L over log L approximation to the value for the high value jobs. And for the other jobs with small fractional allocation, we are going to group them as blocks, and each job has a small enough allocation, which is log L over log L, and each block is just going to contain O of log L consecutive levels, and in each block, the total fractional allocation is at most 1. So this finished the reduction showing that there exists an algorithm that do the meta item partitioning that achieves log L over log L approximation to the fractional optimal solution. Yeah. So another thing I want to talk about is the single-minded setting. So for the single-minded setting, I'm considering the item pricing and ask whether item pricing can route the optimal solution. This was considered to be the Tobul's problem in the history, and we're going to study it for arbitrary graphs. So this is joint work with Zihan Tan from Rutgers University, who is going to be a professor there, and Mingfei Zhao from Google. So for the single-minded buyer, again, we want to ask how to price those edges on the graph. And the benchmark is still the offline optimal. There have been studies on the graph before. So there was a paper in Foxhole 8 showing that for the path graph, item pricing can actually just route the optimal solution. And we provide some results on different other graphs. For example, some tree graphs, we get tied through 2 approximation. For the cycles, we get 2 approximation. Also consider some interesting graph in the graph theory, such as autoplanar graphs. We get a polylog n approximation via item pricing, and we also gave a existential hardness result for grids or general graph, showing that on grids, there's no way that you can route the paths even when the buyer has a fixed value and a fixed arrival. So like any algorithm any item pricing algorithm need to have a omega polynomial and compare ratio. But actually, the interesting thing I want to show today is not on this. So I want to get back to the interval scheduling problem on the path graph and like describe how item pricing can route this optimal solution. So when we look at the fractional relaxation of this online scheduling problem, we can take the dual LP. The dual LP has this form where I just use PI as the dual variables. So why do I use PI as the dual variables? Because those PI just correspond to the item prices that can route the optimal solution. So when we check the dual pricing due to complementary slackness, if a job has allocation at least 0 in the primal LP, it can actually afford the dual price because the dual constraint is going to bind. So although the constraint is saying that the sum of the price is at least the value, actually for the jobs with the positive allocation, the sum of price equals to the value. So the buyer can actually afford it. And if the if the item has a positive price, then it is actually fully allocated. This is shown by the complementary slackness on the constraint of xi in the primal LP. So if the primal LP has an integral optimal solution, then we know that dual price can actually allocate the job with positive allocation. Because all of the jobs in the integral optimal solution is going to have 0 utility. So they have 0 utility, and the seller can just allocate them with tie-breaking power at hand. What this means that when the job has 0 utility, the seller can decide whether to allocate the items to the buyer or not. But this is a weird thing because like the buyers actually don't care about whether they're going to be allocated or not. So how do we prove that the problem has the integral optimal solution? Is that for this primal LP, when we have this constraint to be AX smaller than B, if B is integral, and we know that if the constraint matrix A is totally unimodular, then every extreme point of the LP has the integral solution. So here, the totally unimodular means that every square submatrix of A has determinant either 0 or plus minus 1. And equivalently, this can be defined by there exists partition of rows such that for each column, the coefficient sum differs by at most 1. So now we get back to the interval scheduling problem. So why does the interval scheduling problem has the integral optimal allocation from this LP? Because the constraint is just something like this. Suppose that I have 3 different intervals that are getting allocated. The first interval has items 2, 3, 4. The second interval has item 1, 2, 3. The third interval has item 3, 4. So like it is actually those all one coefficients are so like the 1 and 0 coefficients look like this, and we can partition the rows to 2 parts easily. That the first part consists of rows with odd index, and the second part consists of rows with even index. And we know that for every column, it's just an interval that the sum of the coefficients between the 2 sets is just at most 1. So this is a special property of the intervals. So this just shows that if the LP has an integral optimal solution, then the dual price can sell the items when the seller has tie-breaking power at hand. But what if the sellers do not have tie-breaking power? So like the because the post-pricing mechanism are like this. So like if you come and see whether you can afford the price, and if you have utility 0, you actually the seller do not know whether you have utility 0 or not. So the tie-breaking power in real life are actually at the hand of the buyer's side. So when the buyers actually have the tie-breaking power at hand, then there's a problem. So suppose that I have this interval allocation problem where the intervals have length 1, 2, and the value of the interval are just the length of the intervals. And depending on whether the seller and the buyer have the tie-breaking power, the welfare can be very different. So if the buyer has tie-breaking power, then actually no item pricing have a welfare greater than 2. So like any item pricing can only route like either both of these shorter intervals or one of the longer intervals. So this is showing that when buyers have tie-breaking power, no item pricing can do better than 2 or 3 opt. And this is a property that was not studied before in the literature. In our work, we show that when the graph is a path graph, if the buyers have tie-breaking power, item pricing can actually obtain a tight 2 or 3 times opt welfare. So it means that like even if we force that the buyers to have positive utility when they want to buy item, we can still obtain a tight 2 or 3 of the optimal welfare. Yeah, I think I still have some time. So the way we prove this is via the structural property of the buyers. So we call a set of edge destroying intervals unique if there does not exist another set of edge destroying intervals such that the 2 of them have the same union. Like for example, the above 2 intervals are not unique because the bottom 2 intervals have the same union as the above 2, and the first and last interval, if we combine them as a set, is actually unique because there's no way to interpret the interval in another way. So we prove that for any unique set of edge destroying interval that can afford the due price, there exists a set of item prices such that any interval in the set has strictly positive utility and any interval not in the set has strictly negative utility. So by this, we know we have forced the tie-breaking power and show that for the unique set of intervals, we can actually sell them via item pricing. The way we get a unique set of intervals is as follows. So we first find an optimal integral allocation with the maximum number of intervals. We make a copy of it, and we 3-color the intervals as follows, such that for the same interval, they are not colored the same color. And if there exists, let's say for the first 2 intervals, if there exists another way to describe this interval, I'm actually going to replace it with another set of interval and set a different color. And this can be done repeatedly. And this process can be done from left to right. And at the end of the process, we can show that any color is unique and can be sold by item pricing, even when the buyers have tie-breaking power. So because we have these 2, so like we have 3 sets of intervals with total value twice of the opt. Like one of the color can be sold with value at least 2 to 3 times opt. We also have some results on other special graphs with when the buyer has tie-breaking power, but like a lot of them are not tight. So to summarize, we described the 2 settings where the pricing mechanism allocates the interval resources near optimally. In the Bayesian setting, we are using the balance bound prices. For the single-minded setting, we use the dual item prices So these two are the two very frequently used pricing in the literature. And we also show that the tie-breaking power influences the combine ratio, and for the future directions, two major directions. So definitely improving the ratio is one direction, but the two major directions is that first, beyond sub-additive values, like interval allocation is one specific case where we have the bias beyond sub-additive values. And what are other bias beyond sub-additive values that you can get a good online welfare versus offline welfare. And the other direction is that is there any other instance in the mechanism design problem where, or the algorithm design problem, where the tie-breaking power actually makes much difference, just the same as in this setting? Yeah, I would like to thank you for listening.
Thank you. Yeah, any questions we can ask? Okay. I think so, yeah. So Yifeng, maybe can you comment, like, so what happens with like bundle pricing in the second setting, like instead of item pricing, any advantage?
Bundle setting, you just think bundle pricing, you just sell those bundles optimally. So like if you want to, for example, if you want to sell the first two bundles and you just bundle this as two, bundle this as one, then you can sell this optimally. I think you can even have like the prices to be 1 minus epsilon or 2 minus epsilon.
So you're saying like you can improve the approximation factor with
I
bundle
think you
pricing?
can just the bundle pricing can just sell optimally.
Oh, even optimally, okay.
Even when the buyer has tie-breaking.
Oh, okay. And generally, do you have any comments on like say bundle versus pricing versus item pricing, like which is more interesting? Like bundle pricing, is it interesting to study more, or is it like not really practical?
Bundle pricing, let me see. So bundle pricing is definitely one type of truthful mechanism. When you have the bundle pricing, sometimes the problem becomes like very easy, and sometimes it's actually not doable in real life. But actually, I think bundle pricing should be important in the mechanism design because like when you go to buy the air tickets, bundle pricing is actually a very important setting.
Sure. Yeah, so Andres has a question. Yeah.
What any of the results extend to like beyond single-minded?
So he's asking if the results extend beyond single-minded settings.
Beyond single-minded setting. Beyond single-minded setting, I think there's one problem. Is that in the Bayesian setting, we prove that even in the tree, you cannot get a polynomial approximation, like for any online algorithm. So this Bayesian setting is like this. It's like the buyer is single-minded, but with some arrival probability. So it's actually a very weak. So it's actually a very simple example. So this means that for more general graph item price or like online algorithm, there should be like hardness results, like not only computationally but also existentially. So and for the interval setting, I think like item pricing can do better if you have a large supply, just using what you did yesterday. So like you just change the you just have the capacity to set to like capacity minus times 1 minus epsilon, then there should be like a positive 1 minus epsilon approximation result. But for a small supply setting, you cannot do better, I think.
Thank you. Okay, if there are no further questions, yeah, let's thank all the speakers for this session again.
Yeah, thanks.
Thank you, everyone. And yeah, we'll resume tomorrow.